Hello everyone, thanks for watching this video. I'm Daehwa Kim, a master's student at KAIST. Today, I will introduce OddEyeCam, which is a practical inside a mobile device tracking system to support body-centric people interaction. This work is done by SIGCHI lab at KAIST in collaboration with Keunwoo Park and my advisor Geehyuk. Nowadays, mobile devices are becoming platforms for various applications. However, their small screen make it difficult for users to use information-rich applications. To overcome this problem, many researchers extensively studied the interaction concept of expanding the interaction space to the vicinity of human body. Users could peep into a virtual workspace through a screen of mobile devices. Also, the users could utilize their kinesthetic sense when navigating around their bodies. Therefore, body-centric people interfaces have gained considerable attention. To support such spatial interfaces, various technical approaches were proposed. One approach was to capture a user's face using a mobile device's front camera. Another vision-based approach captured motion of non-body features using rear camera. Another approach utilized the motion data obtained from an accelerometer, gyrosensor, and magnetometer. However, these approaches do not track the user's body position. Therefore, reliable position tracking in body-centered interfaces is difficult when the user is walking or user's head and body is misaligned. Moreover, recent neuropsychological studies found that the human perceives the trunk-centered space as a whole body-centered space rather than a head-centered space. In response, we propose OddEyeCam, which tracks the body as a reference frame. Similar to an OddEye cat with two eyes of different colors, we combine two cameras with different characteristics. Despite the depth camera's useful function, its field of view is too narrow to capture a polypolar scene. A narrow view camera misses a significant portion of body when it is close to the body. Therefore, OddEyeCam finds the body key points from a wide view RGB camera. And then, partial depth information around the user's trunk is obtained from a depth camera to estimate the device position relative to the body. Recently, many mobile devices include a TOF depth camera and a wide view RGB camera. OddEyeCam is expected to be a practical method to support body-centric people interaction for mobile devices. Considering the limitations of earlier work, we set up 4 design goals. First, OddEyeCam has to estimate the absolute location of mobile device relative to the body. Second, to cover various interaction scenarios, OddEyeCam has to continuously track device location in a wide interaction space around the body. Third, our system must robustly estimate the mobile device's location without restricting the user's behavior. Fourth, to completely support the mobile device's portability, OddEyeCam must track the device position relative to the body even when user is moving. We implemented the OddEyeCam prototype using 2 cameras. We attached a 180 degrees fisheye camera and an RGB depth camera to the mobile device. The wide-angle camera provides a whole body image, and the depth camera provides depth information around the user's body. This is the overall pipeline of OddEyeCam. Inputs are wide view RGB image and a narrow view depth image. The output is the position of the mobile device relative to the body. In the camera fusion module, we transform the wide view image to match the narrow view depth image. From now on, I will explain how we matched these 2 images. We have 2 images taken from 2 cameras. Our goal is to combine useful information in each image. We apply the equirectangular projection to the fisheye image to alleviate the distortion of it. The pose estimation module finds body key points on this image. While a normal RGB camera uses a pinhole camera model, a fisheye camera uses an omnidirectional camera model. We applied perspective projection to the wide view image. As shown in two checkerboard images below, we could transform the wide view image like a normal field of view image. We placed the checkerboard sheet at 40 cm from the camera and obtained the homography matrix using the features on the surface taken by two cameras. The wide view image was cropped, transformed, and rotated to match the depth image. Finally, the body key points on the wide view image could be found in the depth image. We estimated the coordinate system of the user's body. The origin of the body coordinate system was the center of two shoulder points. The x-axis was estimated by fitting the 3D points on the line from the left shoulder to the right shoulder. To set a y-axis as a foot-to-head direction, we used the direction of gravity, which is measured using a built-in accelerometer of the mobile device. The z-axis was obtained as a cross product of the x-axis and y-axis. Finally, we can track the device position relative to the body. We quantitatively evaluated our system through 3 experiments. First of all, we conducted a tracking accuracy test. In this test, we evaluated how accurately OddEyeCam could estimate the XYZ position of the mobile device compared with OptiTrack motion capture system. We asked participants to move the mobile device freely and evenly in the space around their bodies. We provided visual aid on the floor and wall to help the participant to move within the boundaries of -60 to +60 degrees. Participants moved the mobile device when they were standing and walking. Participants walked back and forth along the 1.5 meter line on the floor. Also, to know the effect up close, we asked the participants wear 2 different ones. All participants wear casual apparel and a coat they brought. The device position estimated by our system and OptiTrack was compared. The 4 figures in the left shows trajectories of the mobile device seen behind from 10 participants. The error bar indicates the Euclidean distance between the mobile device position estimated by OddEyeCam and OptiTrack. The numbers in 4 figures indicate an average Euclidean distance. Whether the participant walked or not did not significantly affect the tracking result of our system. However, we observed increasing X-position error when participants were wearing a coat. When the camera shoots the user from the side, the thick clothes hide the shoulder and the camera could not capture the hidden part. In the second experiment, we checked whether OddEyeCam satisfies our design goals and whether it was sufficient for various body-centric peephole interfaces. We divided the design spaces into 6 subspaces to cover various design possibilities of OddEyeCam. The table below shows design spaces in combination of the user's walking state, current mobile device's input, and OddEyeCam. The participants use these example applications and perform simple subtasks. From now on, I will briefly describe the application that the participant used in this user study. A photo app and a messenger app was in front of the participant. Participants could drag the photo and drop it on the messenger app. We implemented a body-centric folder, and the participant could access each folder by placing the smartphone at each location. A user could select an app by tilting the device. A world map was in front of the participants. If the participants brought the device closer to the map, the device peeped into the partial region of the map, which is zoomed in. For one-hand tagging application, 9 tagging zones surrounded the participant. Participants could drag the notification from the closer layer and then drop it to the tagging zone in the farther layer. We implemented a Getting Direction app, which provides different information depending on the participant's walking state. When the user stands still, this application provides information about the destination, such as nearby restaurant or hotels. Or it gives participants how to reach the destination when they walk. We built a 2-step marking menu so that the participant can trigger body-attached shortcuts while paying less visual attention. After using each application in the standing and walking situations, each participant scored statements with a 7-point Likert scale. The statements were related to our design goals. The result shows that the participant felt continuous movement and felt like they moved the peephole over the body-fixed contents. Also, they could use the contents in the same location after long usage periods and could retrieve the desired contents even in instantaneous access. The participants could access and interact with the body-fixed contents while they walked. The participants reported that they could easily tag the notifications because they could remember the location of the contents relative to the body even when they were walking. The third experiment is the quantitative characterization of OddEyeCam. To characterize our system and understand the capabilities of OddEyeCam, we conducted people target acquisition tasks on OddEyeCam. Participants could peep into the target through the device screen and then select the target using their holding hand's thumb. Participants conducted the task in both standing and walking situations. The human's target selection skill follows Fitts law. To verify the usability of OddEyeCam, it is meaningful to confirm whether participants' target selection using OddEyeCam follows Fitts law or not. From 12 participants' data, OddEyeCam follows Fitts law for both standing and walking situations. In other words, OddEyeCam could support the natural human arm and hand movements in people target pointing tasks. The overall error rates were 7.7% for the standing situation and 18.8% for the walking situation. High error rates were concentrated at the small target width. Now, let me summarize this presentation. We proposed a practical inside a mobile device tracking system to support body-centric peephole interaction. OddEyeCam could track the mobile device's 3D location in an absolute manner in both static and mobile environments with an average error of 4.3 cm. The participants could use various body-centric peephole interaction scenarios on OddEyeCam, and these scenarios required continuous tracking in a large 3D space around the user's body. The peephole target selection task on OddEyeCam followed Fitts law, and this suggests that OddEyeCam could support the natural human hand movement. This is the end of my presentation. Please see our paper for more details. And also, please feel free to contact the authors through the below information. Thank you for listening.